Our project is called Newgenes. It is a 15-watt edge-deployable large language model that takes natural language as input and output a valid SBOL3 design. Our goals and motivation came from several problems we identified on the current SBOL design process. So traditionally, if you want to design a genetic circuit, you would either have to draw it on a GUI or program it yourself, which could be time-consuming, and it's difficult for people who are unfamiliar with programming genetic circuits. And now there are powerful large language models, but they only live in cloud and are expensive to use as you scale up the designs. And sometimes you don't want to disclose your design online or worry about safety of your data, or you don't have enough budget to use frontier LLMs, or just want to use it for educational purposes. And therefore, we want to build a product that runs locally, takes natural language, and turns it into a valid SBOL3 design at no additional cost. And the ultimate vision for the real-life usage of this project would be possibly be in wet lab settings, where you could be working on some experiments and an idea suddenly pops into your mind. But you don't want to disrupt your workflow, or you want to envision the circuit really fast just to check if it works. So then you would use Newgenes. You enter a prompt and say something like, I want X to do Y when Z happens, using the following parts available in the lab. And then 45 seconds later, you'll get a valid SBOL3 XML file, which you can then use to feed it into any graphic or SBOL graphic visualizer to check it. So the whole process should be free, fast, and doesn't require any internet, and none of your data leaves the device. So the short functionality, the whole pipeline breaks down into 3 major steps. First, you will enter a prompt, and then second, the large language model takes your prompt, and the third step is it's gonna output a valid XML file, and then we check it by using PySBOL3 and then iBiosim for structure and grammars.
This is the training data we use to train our models. We have more than 1,000 examples, and we've separated them into 3 tiers. The tier 1 was for the simple circuit, with a model called Qwen 2.572 billions to run locally to generate the simple circuit. And for the tier 2, we use the GPT 5.4 APIs to generate the relatively more complex circuits. And besides all that, we also use the API to do some repair work to the simple circuits we generated before. And for the tier 3, we scrapped some of the circuits from the literature, SynBioHub, iGEM, and data curation project. And in terms of the format of the training data, we have a chat-style JSON files and separate them into 3 sections: the system, user, assistant. And for the system, it was the identical prompts we used to trick the model into a certain realm, so the models know where the training data is going to be and how the output is going to retrace into the system prompt. And the user, it was the prompt we backtraced from the circuits using GPT 5.4 API. And for the assistant, it was the circuits, the components, and its interactions, and so on. And besides of the training data, we also have we generated 100 evaluation prompts. Additionally, we did a contamination check for the 100 evaluation prompts with the training data we have, and the result shows it doesn't overlap, so the results for the evaluation will be much more valid than before. These are the 2 ways we use to improve our output quality. The first one is the LoRa. It was basically how we used the training data we got before to train the large language models in terms of the low rank trainings. And the second one was the train-trans assay. We scroll through the assay and we conclude 5 aspects we can use to generate our own sort of constraint prompts, which is roughly 5,000 characters long, to input to the large language model before even the user inputting their own prompts. And both of the methods are used to improving the quality of the outputs, and our results has demonstrated some significant impact and positive trend in terms of the progress. This is our rubric to evaluate the performance of the large language models. We have 6 deterministic axes, 100 points, and all of it are pure Python. Axis 1, structural validity, 20 points. Is the JSON internally coherent? Parses cleanly. Reference resolved. No self-loops. Axis 2, behavioral wiring, 20 points. Are the right parts to driving the right interactions? Transcription from promoters. Translation from RBASs. Every coding sequence terminated. Axis 3, biology appropriate, 20 points. Are the parts real and organism compatible? No T7 in mammalian. No SIM with E. coli. No hallucinated BBA names. Axis 4, part fidelity, 20 points. Did the model deliver what the prompt asked for? Right organisms, require parse present. Gate topology matches the spec. Axis 5, description quality, 10 points. Readable, snake case, modular, no duplicates. Axis 6, response format, 10 points. Is it sensibly engineered? Feedback only when requested. Burden on the 20 components. Chassis appropriate. Same exam every model. Fully reproducible. This is our Jetson Orin, and here's us running the large language model on Jetsons. And that's our prompt. Let's hit enter. And one more time. It's all running, and let's wait like a couple minutes. It's gonna probably take a bit longer than the MacBook. And it's not completed. Here's the SBOL file we got from the JSON files right here. Here's the JSON files, and here's the score. We got 90 of 100 according to our rubric. And here's the ontology mapping and the validation. We're now running the large language model on MacBook, which is a little bit more robust model compared to what I was running on the Jetsons. And we're doing the same prompt. Let's hit enter. And one more time. You can see the improvement in the speed because the chip on the MacBook is a bit newer than the Jetsons. Here it completes, and let's go see the score. We got a 91, slightly higher than the Jetsons, and everything works perfectly here. You can see the ontology mappings, the SBOL3 validations, and all the SBOL3 files right here. After running against the 100 prompts rubric, both model performs fairly well. The Jetsons hits an average of 89.6, while the MacBook hits an average of 92.2. Both devices shows a concrete result, showing the feasibility of the workflow of using large language model to perform and generate SBOL3 outputs.